All right, career night is tonight. Reminder. 7 o'clock, CC 313. You can get 5 points of extra credit towards your homework score if you come on time, stay awake, and stay the whole time. Otherwise, you get partial credit for that if you can't make it on time. Otherwise, if you can't make it, you can do section 9.4, number 70, though you should not only get the correct answer, you should give reasons. It's a series, you get to decide about convergence, and you should give reasons for your answers, and they should be valid reasons to get the full extra credit. So it will be graded that way. It's not a super hard problem, so you should be able to get it, but do give reasons. As an alternative way to get extra credit, turn it in on Wednesday in a separate pile up front from the rest of the homework so I can make sure those are separate from each other. No extra credit for both because there would be some people who can't do both, so it's one or the other to do. All right, 2 lectures again. Lecture A, briefly want to review absolute versus non-absolute or conditional convergence. And then we get back into Taylor polynomials, and then lecture B, Taylor series, various methods of calculation. We do lots of examples. Actually, you probably consider Taylor series as being part of lecture A as well. All right, but what is the difference again between absolute and non-absolute convergence? I wrote some definitions on the board last time. Let's just consider a couple examples. We'll consider alternating series, but they don't have to be alternating series. So this is an alternating series that looks like this. Does it converge or not first? Does that converge or not? It's an alternating series, that's a hint. That word alternating. Yes, it does. There's an alternating series test that says if you look at the absolute values of these terms, and those form a positive decreasing sequence that goes to 0 as k goes to infinity. And because the signs are alternating, plus, minus, plus, minus, plus, minus, or it could be minus, plus, minus, plus, minus, plus as well, this must be then a convergent series, the alternating series test. It is also what's called absolutely convergent, because the series whose terms are these things right here converges as well. It's a p-series with p equal to 2. The absolute values of the terms of the original series give you this series. That's a p-series with p equal to 2. We know that converges. That means not only does this original series converge, it also converges absolutely. What's the big deal about that? The big deal is with absolutely convergent series, they're more robust. We can, for example, rearrange the terms if we want. We can do some algebra with them, and we still get a new series that converges to the same thing. So they're stronger or more robust that way. Contrast this with a non-absolutely convergent series, the most famous example of which is the alternating harmonic series. I made the k squared now just a k. That series does converge by the alternating series test. It's an alternating series first of all, and the absolute values of its terms forms a sequence of positive numbers that decreases towards 0 as k goes to infinity. Those conditions are enough to imply that this converges. And we saw it actually converges to natural log of 2. However, it is not absolutely convergent. It is conditionally convergent, is the word the book uses. I actually say non-absolutely convergent, because the series whose terms are its absolute values, the absolute values of the terms of this one, is the actual harmonic series, which we know diverges. That diverges. Therefore, even though this converges, it converges conditionally, non-absolutely. And that's a more fragile kind of convergence. It turns out you can, for example, rearrange the terms of such a series to make the new series converge to any number you want, even a million or a billion, whatever. That seems not good. It's interesting, but it seems not good. The commutative property for that kind of infinite series evidently would not work. Okay? So that's more fragile, kind of not as good in a sense. All right. It's going to turn out that power series and Taylor series are power series, they're special kind of power series. On their interval of convergence, the convergence will be absolute for values of x inside the interval of convergence. At least in the interior, not the endpoints, I should say. Not necessarily the endpoints. All right, let's go back to computations with Taylor polynomials and Taylor series. I'm going to show you a lot of tricks today, tricks of the trade for computing these things in various kinds of ways. You do not always have to use that formula for a Taylor series or a Taylor polynomial. The Taylor polynomial of a nice function f of a certain degree, degree n, at x equals a, we've been calling p sub n of x, that's what the book calls it. In the summation formula, if the sum k goes from 0 to infinity of the kth derivative of f at a divided by k factorial, oops, not to infinity, this is a polynomial. Go up to n here. The kth derivative of f, that's what that notation means. It's not the kth power, it's the kth derivative of f at a divided by k factorial times x minus a to the k power. It's good to write this out as well. It helps people understand it better, I think. A, again, is a fixed number. Actually, when k is 0, the 0th derivative of f is taken to be f itself. 0 factorial, by definition, is 1. So the first term is actually just f of a. We got a 0th power there, so you get 1 there with x minus a to the k. The only thing that's not 1 is f of a with the first term when k is 0. When k is 1, I get f prime of a, first derivative, divided by 1 factorial. 1 factorial is also 1, so we don't need to write it, times x minus a to the first, f prime of a times x minus a. I think this is zoomed in enough to see that. Oh, I hope. Well, I'm writing this is how big it is. Look good? Okay. Yeah. When k is 2, I get the second derivative at a divided by 2 factorial times x minus a squared. Then it would be the third derivative of f at a divided by 3 factorial times x minus a to the third. Let's go ahead and write that. The last one would be when k is n, the nth derivative of f at a divided by n factorial times x minus a to the n. So this would be a Taylor polynomial of degree n, centered at x equals a, and the goal is to approximate f. Why does this approximate f near a? I tried going through the details of the computation with the previous class, and it got to be so much of a mess that I don't think I'm going to go through it again with you guys. But suffice it to say that if you take the kth derivative of this polynomial at a, it equals the kth derivative of f at a. So you're matching up the function values. The function value when k is 0 is the actual function value, f of a equals p n of a. You're matching the derivatives, the slope of the tangent line for these functions. You're matching up the concavity with the second derivative, and higher derivatives are getting matched up at a as well. This is when k is between 0 and n. If k is bigger than n, then this is not true, because the higher derivatives of f at a are not necessarily 0, but a higher derivative of this thing past the nth derivative would be 0 because this is an nth degree polynomial. Okay, let's do some examples with Mathematica to help us, and some by hand, and we'll see that this formula works. Actually, the initial one, let's start to do by hand, so I'm going to come over to this board if you want to move it a little bit. Let's consider this example, f of x equals 1 over 1 plus x squared. I could use this formula to find the Taylor polynomial of any degree that I want. However, that is kind of a pain. I'd have to take a bunch of derivatives of this thing, and you might imagine that those derivatives get kind of messy. You use the quotient rule here. You also could use the chain rule if you write it like this. They do get kind of messy. So instead of that, I'm going to use a trick. Same trick I've shown you last week. I'm going to recognize that this can be put in the form a over 1 minus r. I can think of it as the sum of the geometric series. And that's going to be a trick to help me find the Taylor series for this centered at 0. This equality was true for the infinite sum as long as the absolute value of r was less than 1. If I just rewrite this function in the form 1 over 1 minus negative x squared, compare this with that, they have the same if a is 1 and r is negative x squared. So now use this formula with a equal to 1 and r equal to negative x squared. You get 1 plus 1 times negative x squared plus 1 times negative x squared squared plus 1 times negative x squared cubed, etc. Simplify it. It simplifies to 1 minus x squared plus x to the 4th minus x to the 6th, etc. The absolute value of r must be less than 1, so this means for this to be true, the absolute value of negative x squared must be less than 1. That's equivalent to saying the absolute value of x squared is less than 1, which is equivalent to saying the absolute value of x quantity squared is less than 1, which is equivalent to saying x itself in absolute value is less than 1. Think about that. If x is somewhere between negative 1 and 1, all these things are going to be true. They mean the same thing. The interval of convergence is the open interval from negative 1 to 1. This is also equivalent to saying x is strictly between negative 1 and 1. That's the interval of convergence centered at 0. It's got a radius of 1. If we use the ratio test to figure out the radius of convergence here, we would get 1. Does this stuff on the board over here give the same answer? Let's have Mathematica do the calculations for us. Define f of x to be 1 over 1 plus x squared. We can see how nasty looking the derivatives get by having Mathematica calculate these derivatives. I'm going to put them in a list, so I'm going to put them inside curly braces separated by commas so that my output is not too long in a vertical stack, but instead goes horizontally. Here's what I mean. I'm going to, inside curly braces, I'm going to have Mathematica calculate these derivatives here. Oh, let's go up through the 6th derivative. Okay, they do get kind of nasty looking. Those could be simplified if you used the command together. Maybe I could probably even do that all at once in there. Once they're in a list, I could go / together to simplify those. Yeah, it simplifies them. Still kind of nasty. There, for example, right here is the sixth derivative of the function. Okay? So it's good we're having the technology doing this instead of doing it by hand. Let's also plug in a. We're taking a to be 0 here, right? Because these x's can be thought of as x minus 0. X squared is x minus 0 quantity squared. X to the fourth is x minus 0 quantity to the fourth. The a is 0 here. So let me also evaluate these things at x equals 0, along with the function value at 0 as well. Let me put that in here too. Plug in a bunch of zeros now. Here's what we get. F of 0 is 1, f prime of 0 is 0, f double prime of 0 is -2, f triple prime of 0 is 0. The fourth derivative of f at 0 is 24, the fifth is 0, and the sixth derivative of f at 0 is -720. If I now divide these all by the appropriate factorials, I get the coefficients for the Taylor series. Divide by 0 factorial is dividing by 1, but I'll put it in here anyway. Same with dividing by 1 factorial. Dividing by 2 factorial is the same as dividing by 2. Dividing by 3 factorial is the same as dividing by 6. 4 factorial is 24. This was a 24 there. 5 factorial. 6 factorial is 720. -720 is there. The coefficients for the Taylor series centered at 0 go 1, 0, -1, 0, 1, 0, -1. The pattern would continue. 1, 0, there is no x term. -1, 0, there is no x cubed term. 1, 0, there is no x to the fifth term. -1, 0, there is no x to the seventh term. The Taylor series formula is giving us the same thing. If we created a Taylor polynomial with this, could I see that matching? And could I also graph it and see how the graphs match? Sure. This was where I was having some trouble with Mathematica in the previous class, but I think I know how to fix it now. So I'm going to program in Mathematica a general Taylor polynomial formula for Pn. We'll use a equals 0 for all of our examples. It's the most common thing to use for a. But you should be flexible enough to deal with other a's as well. So I won't bother putting an a in this notation, but I will put an a here. There's f of a. Then I'm going to use the summation button. K goes from 1 to n. This is the Taylor polynomial formula. I'm putting the f of a there in front of the summation because last week, when I tried to put it in the summation with k equals 0 there, I ran into trouble when I plugged in a because Mathematica tried to compute 0 to the 0 power, which is undefined. So this is a little trick to avoid that problem. Just put the f of a there in the beginning. I am going to divide by k factorial and multiply times x minus a to the kth power. Actually, you know, maybe I shouldn't put a general a in here. Let's just do 0. So a is going to be 0 here. But what goes up top there? It's the kth derivative of f at 0. How do you type in k primes? You can't. Here's the way to deal with it. D will calculate a derivative, and not just a regular derivative, but even if I want a second, third, or fourth, or fifth derivative of f of x with respect to x. And if I want the kth derivative, I need to put a comma k right there inside a curly brace. This calculates the kth derivative of f at x. This is not notation you have to be able to use in this class. For some future math classes you might want to use it, but I'm showing it to you. That's how to calculate the kth derivative. If you then want to plug in x equals 0 after you've calculated the kth derivative, you have to do another little trick. You need to do slash dot in curly braces x arrow 0. Essentially, this is a fancy way of saying plug in 0 after you've taken the kth derivative, which is part of the formula, right? On the screen back here. Plug in a into the kth derivative. A is 0. That's what I'm doing. This calculates the derivative. This plugs in 0 after calculating the derivative. So now, for example, with the given function f plugged in there, I can calculate p6 of x and get the same answer we got before. Same answer is on the board. This was an infinite series here, going on forever. You see over here? And on Mathematica, we've got not an infinite Taylor series, but instead a Taylor polynomial. It's a finite sum. This is an infinite sum. So they're not equal to each other, but you do see the terms up through the 6th power do match. Now we can look at the graphs of these things and manipulate it. Manipulate, plot, f of x, p sub n of x, near x equals 0. Like -1 to 1 would be the interval of convergence. Let's just go ahead and graph it on that domain here initially. The original function is going to be blue, and the Taylor polynomial will be red. I let n increase here, like this. Something's wrong here. What is wrong? Does it not like my Pn of x? Let's see. Let me try. Sometimes if you run into this kind of trouble, it's good to clear Mathematica's memory. Go to the palettes menu, or evaluation menu, quick kernel, and that'll erase its memory. I'm not sure if this is going to help or not. Let's try it. Now we're still running into problems. I'm not sure what the problem is. I thought I fixed all the problems from the previous class. I'm not sure what the problem is. I don't think the fact that n is a subscript is a problem. P6 is that. P8 is this. X doesn't have a value. If I plug in x here, do I get something? I think my syntax looks good. Let's see a problem. Using underscores. Oh boy. I'm not sure what the problem is. I did plug in 0 into this. After taking the derivative, I was doing something like this in the previous class. I didn't try graphing it. Maybe that's why I didn't try to run into trouble in the previous class. Okay, well, let's not worry about the graph then. We can see the graph. The Taylor polynomials approaching the graph of the original function. I'm not sure what I did wrong. I'll see if I can fix it before next time. Okay? But we did see the formula look right. That looks right. Let's try another example. There are various tricks you can do with Taylor series. One of them is just using geometric series formulas, sometimes after a little bit of algebraic creativity. Another thing you can do is you can differentiate them and integrate them term by term, at least inside the interval of convergence, possibly not at the endpoints. Let's do that here with this example. The integral of 1 over 1 plus x squared, if we believe that you can integrate by term, would be the same as the integral of the infinite series. I guess I haven't used the fact that I'm saying you can integrate term by term yet. Which is going to be some constant of integration, c plus x minus 1/3 x cubed plus 1/5 x to the 5th minus 1/7 x to the 7th, etc. I integrated term by term in that last step there, where c is a constant of integration. Is this a good idea? Evidently, this must be then a series for what? What's the integral of 1 over 1 plus x squared? Gateway, memorized integral. Arctangent of x plus c. But when you do an indefinite integral on two sides of an equation, you can put the c on just one side. However, since arctangent of 0 is 0, you can take the c to be 0. Because if you plug in x equals 0 here, you get a bunch of zeros. So in fact, evidently, arctangent of x is x minus 1/3 x cubed plus 1/5 x to the 5th minus 1/7 x to the 7th, etc. as an infinite series, an infinite Taylor polynomial. That we can truncate to any degree we want to get a finite Taylor. This is an infinite Taylor series. We can truncate this anywhere we want to get a finite Taylor polynomial of degree 7, for example. Constructed in such a way to make the derivatives of these things match up at 0. The graph of this and any finite truncation should be pretty close together when x is 0. And in fact, the infinite sum equals the arctangent function, not over the entire real number line, though. This equation over here was true when x was strictly between -1 and 1. The interval of convergence was -1 to 1, and that was where these things were equal. It does turn out, almost as if by magic, that this converges at one more point of the arctangent function. You can include x equals 1 as part of the domain where this works. This converges and is a true equation when x is strictly bigger than -1 but less than or equal to +1. We added 1 point, x equals 1, to the interval of convergence. Not a real big deal. Though historically it was actually a big deal because it would imply that arctangent of 1 is 1 minus 1/3 plus 1/5 minus 1/7, etc. But arctangent of 1, I hope you remember, is pi over 4. It's the angle whose tangent is 1, that's 45 degrees, pi over 4 in radians. And therefore, evidently, pi is 4 minus 4/3 plus 4/5 minus 4/7, etc. We can represent pi as an infinite sum that way. Interesting. And that was kind of a revelation when it was discovered. And people did use this summation to try to approximate pi. However, the convergence is excruciatingly slow. It's a conditionally convergent series with very slow convergence. It does converge by the alternating series test, but very, very slowly to pi. It's not super practical, even though you can use it to approximate pi. There are better methods, though, that still involve infinite series. And again, nobody literally adds up infinitely many numbers. You stop somewhere. You have some finite truncation approximation to the thing you're after, because nobody can do it forever. Not even computers, right? It is true that the infinite sum equals pi, but you can't actually do the sum forever. If you can integrate series term by term to get from here to here, does that mean you can differentiate series term by term as well? I'll do that and then we'll take our break. What if I differentiated both sides of this equation? F prime of x, the derivative of 1 over 1 plus x squared, as an infinite series must be the derivative of this thing. Differentiate term by term. Does it really work? Can you do that? It does turn out that on the interior of the interval of convergence you can get negative 2x plus 4x cubed minus 6x to the fifth. But what does that tell you? It tells you that's a series representation of the derivative of 1 over 1 plus x squared, which by, say, the power rule and chain rule is also equal to negative 1 plus x squared to the negative 2 times 2x, negative 2x over 1 plus x squared squared. This is the Taylor series for that function. After break, we'll check that this is correct, and we'll also divide both sides of this equation by negative 2x to get the Taylor series for 1 over 1 plus x squared squared, which would be a simpler function to focus on. We'll take a break now, though.